Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
This video will show you how to use static equilibrium to calculate the reactions for this simple beam. This is the first in a series of short videos that together introduce internal forces in beams. So, let's get started. We're looking at a simply supported beam carrying 2-point loads. It has a knife edge support at A and a roller support at C. We're interested in calculating reactions, so start by drawing a free body diagram bubble that cuts the structure away from its supports. That requires 2 cuts, one at support A and one at support C. The free body diagram bubble helps you to define what goes into the free body diagram and what forces are released by the cuts. If you're unfamiliar with free body diagrams and free body diagram bubbles, then shame on you. Sorry, only joking. What you really need to do is click the link at the top of the screen. It's worth doing because they're uber important. Having drawn the bubble, the next step is to draw the free body diagram showing everything inside the bubble. That's the beam itself, the applied loads, and we must also include any internal forces that have been exposed by the cuts. You can think of the reactive forces at A and C as being hidden until exposed by the cuts made to create the free body. A word on supports. The support at A is what's known as a knife edge support. Such supports prevent horizontal and vertical displacement, but allow rotation. And to do this, they supply horizontal and vertical components of reaction. At C, there is a roller support that prevents vertical displacement at C by providing vertical force. Notice, for convenience, the 50 kN force has been resolved into horizontal and vertical components. Note also, the directions assumed for the unknown forces just does not matter. Assume a direction and let the arithmetic sort it out. If the chosen direction is wrong, then the arithmetic will tell you by assigning a negative value to it. Having said that, I usually try to get the directions correct. It's a good way to improve your understanding of how structures work. If you're wrong, the arithmetic will always tell you. The next step is to use equilibrium equations to find the unknown forces. We're dealing with a structure where both the structure itself and the loads lie in a single plane. That is the plane of your screen. Such structures are known as plane structures. The structure is assumed to be in a state of static equilibrium. In other words, the structure is stationary, so no inertia forces are involved. There are 3 equilibrium equations that apply when analysing plane structures. These equations are commonly expressed as horizontal forces must sum to 0, vertical forces must sum to 0, and moments about any point must also sum to 0. I suggest that you pause the playback and think about where to start. Inspection of the free body shows that horizontal equilibrium will yield the horizontal reaction at A. It makes sense to pick the low-hanging fruit first. And when it comes to writing equilibrium equations, always start by writing down what you're doing. First, state the sum of horizontal forces must equal 0, and that horizontal forces acting to the right will be regarded as positive. That's the sign convention we're going to use for this equation. Solving the resulting equation shows HA, the horizontal reaction, is minus 30 kilonewtons. The negative sign indicates that the assumed direction for HA is wrong. In other words, HA is 30 kilonewtons acting to the left. We now need to decide what next to do. Any ideas? Well, vertical equilibrium would not get us very far. Why? Well, inspection of the Freebody diagram shows that vertical equilibrium would involve two unknowns, VA and VC. One equation with two unknowns does not have a unique solution. And that's no good. No, it's better to use moments. But about which point? That's always the question. Looking at the Freebody, we see that if we take moments about either A or C, only one of the vertical reactions will appear in our moment equation, and that's a good thing. One equation with one unknown is just what we like to see. So let's take turning effects about A. This will eliminate VA from the equation as it has a lever arm of 0. Again, always start by saying what you're doing. State that moments about A must sum to 0 and that we're going to regard anticlockwise turning effects as positive. Notice, when dealing with the influence of forces acting at a distance, I often talk about turning effects rather than moments. Moments and turning effects are the same thing, but I find that some people become confused by the difference between bending moments and turning effects. Try not to be one of these people. And when summing turning effects, work systematically from one side of the structure to the other. That way, the chance of missing out a force is reduced. So, working from left to right, the first force that has a turning effect is the 40 kilonewton vertical force. First, write down the force, then multiply it by its lever arm, and finally add the sign indicating if the turning effect is clockwise or counterclockwise. And we do this for all forces. The turning effect of the 40 kilonewton force is clockwise, so it is negative according to our chosen sign convention. The 30 kilonewton force has a lever arm of 0 as it passes through A, so its turning effect is 0 and consequently it can be ignored in this calculation. The next force that we encounter is the unknown vertical reaction VC. It has a 10 meter lever arm and an anti-clockwise turning effect about A, so it's positive. And finally, there's a negative turning effect due to the 25 kilonewton force with a 14 meter lever arm. Tidying up the resulting equation yields VC as 55 kilonewtons. It's positive, so our assumed force direction is correct. Finally, calculate VA by summing vertical forces. For equilibrium, vertical forces must sum to 0, and we will regard upwards forces as positive. Now write down the vertical forces, remembering that we have already determined that VC is plus 55 kilonewtons. Solving the resulting equation shows that VA is plus 10 kilonewtons. In other words, 10 kilonewtons acting upwards. Well, that completes the analysis. Not too tricky. But be aware, there's always a number of ways to solve the equilibrium equations. Our solution was simple because we made good choices. To illustrate, let's explore what happens if vertical forces are summed after calculating the horizontal reaction. A bad decision because it results in an equation with two unknowns. So we need another equation. Now, compound the felony by taking moments about B. Sadly, one bad choice after another. Why? Because this results in another equation with two unknowns. This amateur hour, I tell you. Okay, it's messy, but there's hope, because we now have two equations involving the same two unknowns, VA and VC. Two equations involving the same two unknowns can be solved simultaneously, and to keep track of what's going on, it makes sense to number the equations. Rearranging equation 2 shows VA is equal to 65 minus VC, and rearranging equation 3 shows VC is equal to VA plus 45. Next, substitute for VC in equation 4 then solve to show that VA is equal to 10 kilonewtons. And finally, substituting for VA in equation 5 shows VC is equal to 55 kilonewtons. This solution has been a lot more work than our original solution. Notice, however, the results were the same. That's the way it works. If you don't make a mistake, that is. Also notice that more work takes more time, and more work means more chance of error. As I said, there's usually a price to pay for bad choices. This is the first of 4 videos introducing internal forces and beam structures. Next video in the series will set up algebraic expressions for axial force, shear force and bending moment in the beam. Woohoo! These expressions will then be used to draw the axial force, shear force and bending moment diagrams. These diagrams play an important role in structural engineering, and because of that, they also play an important part in structural engineering exam papers. Just saying. If you would like an annotated printable copy of this solution, then head over to Dr. Jim's website, drjimstructures.com. There's a link below. If you found this video useful, please give it a like and consider subscribing to Dr. Jim's Structures channel. And please feel free to add your comments and questions. Well, thanks for watching. Bye for now, and I hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.